We're going to take a look at the concept of an integral value versus an area value. This is something we've probably already talked about in class, and I know we're going to end up talking about this more as we go throughout the course, but it's an important distinction because an integral value is really based very much on trapped area, and these two numbers, these two answers, are not always the same thing, but sometimes they are the same thing. So we're going to go through a series of examples here to show you the difference. So I have a very friendly function, negative 2/3 x plus 2, and we're going to go from an x equals negative 3 all the way over to an x equals 6. If I wanted to do the integral of this function, my answer would be 9. And what's really happening here is we're getting area trapped between the function and the x-axis there, and then as we cross over into negative territory, the area between the function and the x-axis is down there. So as you know from integral properties, as I travel from negative 3 over to 6, I'm heading to the right, and this area is above the x-axis, so the integral counts all of this as positive. But as I go to this section, I'm traveling to the right, but the area is below the x-axis, so the integral counts all of this as negative. You net those two together, whether or not you know this positive negative stuff, you get an answer of 9. You either get that by going to your calculator or doing a nice friendly integration by hand. So by the way, if you want a little practice, this is a pretty easy, straightforward one, but students always have trouble with integration by hand. So go ahead and work that out by hand, and then you can compare it to my work here. And I'm not going to leave it sitting up here because you can easily pause this thing. Bottom line is, we have ourselves an integral value of 9. But if I want to look at the area value, that's going to be something very different, because area cannot be negative. Area is only positive. You don't live in a negative 120 square foot bedroom. So for this region, it's represented by that triangle with an area of 12. This region, the integral is going to treat this as negative, but not us for area, because area can't be negative. So I have a 3 by 2 triangle for an area of 3. So my area 12, my area 3 goes to a total amount of trapped area of 15, even though the integral counted it as 9, because the integral did a positive 12 combined with a negative 3. I'm going to take that same idea and with two different examples provide a little bit more spice. This would definitely be a calculator problem. And we have the curvy function e to the x minus 5. And so I did a graph of it, but it's certainly not to scale. And we just want to go from 0 to 3 along the x-axis. So if I wanted to find my trapped area, I would be aware that that's going to be very different than the integral value in this case, because we're mixing some positives and some negatives. Your first order of business would be to find out, when does this graph intersect the x-axis? Because that's going to be the borderline between an integral on one part and an integral on the other part. I find out where it intersects the x-axis. And now the difference between this problem and the previous problem is these two compartments are not beautiful little triangles that we can do based on geometry when we do the total area. So let's begin with just the integral value. The integral value would be very simply the integral from 0 to 3 of this function. The magic of calculus does all of the positive, minus, and all that stuff for you, and we end up with a 4.086 integral value. By the way, the fact that that integral is positive tells me that I must have more positive area than negative, or than area trapped below the x-axis. So my drawing is definitely probably not to scale. But now if I wanted to do the area, I really have to think of these two separate compartments. So this compartment right here is represented by this integral 0 to 1.609 blah blah blah, because that's the intersection point I found. We have to do this as an integral because it's not a convenient triangle. Same thing with this compartment. Now I start at 1.609 and I go all the way over to 3. And you'll notice that the amount of area I have here is 4.04719. The integral likes to call it negative, but the actual area is 4.04179. This is an area a little bit more than 8, so I combine my two areas and I have my total trapped area. Same thing really as the previous example, but the equation was a little bit rougher, so we couldn't rely on our geometry. We had to use integration to find area. Now for the last problem, and we're not going to do a ton of calculations here, but this one is definitely a twist, and you have to be ready for this because with area problems, there's no set procedure or set formulaic type of problem. You just kind of have to roll with it no matter which way it goes. So now we're looking for this area. You'll notice this is different than stuff we've done before because that's not area trapped between a function and the x-axis. So we need a different way to look at it. Now one thing I do know, this area right here, I'm shading it in yellow. Yeah, that's kind of visible. All right. So that really would be an integral because it's area trapped between this function, negative x squared plus 9, and the x-axis. So we're going to use that to our advantage. But I need this red speckled area, and what I would recommend in a case like this, although you might know another way, is what I would call caveman hieroglyphics. That sliver that I'm looking for is really this one full rectangle minus this crescent in yellow. Well, this yellow crescent, like I said before, that's just regular old integration. This is regular old geometry. So by doing this caveman hieroglyphics, I'm really doing addition and subtraction with geometric figures, I can get my answer. This entire rectangle has an area of 27. This piece, via integration, has an area of 18. So I put those two ideas together and I get a total trapped area of the red speckled area of 9. This has been integral value versus trapped area, and we will be revisiting this in at least 2 or 3 other ways, shapes, or forms as we go throughout the course.